Hello everyone, welcome to this presentation on modeling and evaluation of biomethane trucks. This project was done at the Center for Sustainable Road Freight, and it was done in collaboration with two industrial partners, John Lewis Partnership and CNG Fuels. This project was funded by Innovate UK for a period of 2.5 years. In this project, we evaluated a gas heavy goods vehicle that can run on either CNG or biomethane and compared it against a diesel heavy goods vehicle. The comparison was done for both transport performance and total cost for the owner. This slide shows how the gas and diesel vehicles were instrumented for this project. At the core of the instrumentation scheme, there is a data logger called SRF logger shown here. It is connected to a truck's FMS interface. Here FMS stands for Fleet Management System. Via this interface, the logger can collect data such as vehicle speed, distance covered, fuel flow rate if it's available, etc. It can also collect the vehicle's GPS coordinates as it's a smartphone-based data logger. Now this logger is connected to a Bluetooth data logger, which is further connected to a diesel flow meter if it is a diesel truck, or to a gas flow meter if it is a gas truck. Here CG stands for compressed gas. Now all this data is sent via mobile internet to a data server at Cambridge. And then we use all this data we could collect in order to model the vehicle. Here we can see the diesel flow meter on the right hand side image and the gas flow meter on the left hand side image. These fuel flow meters were instrumented on the vehicles so that we can get more accurate measurements which we could use to model the vehicle. This slide shows the fuel consumption model which we developed using the data we collected. The model has two inputs, a vehicle speed profile input and a road elevation input. The model has one output, that is the total fuel consumed. It can be the gas consumed or diesel consumed depending on which vehicle type it is. The model has mainly 5 blocks. The first block is a driver block which determines how much throttle or brake input is needed in order to follow the speed profile we have. Then there is an engine power profile block which determines how much power is needed from the engine. Then there is an engine fuel flow rate block which determines how much fuel flow rate is needed. Then there is an integration block which integrates the fuel flow rate so that we can calculate the total fuel consumption needed. There is also a vehicle motion block which calculates the equations of motion for the vehicle so that we can update the vehicle speed, which is then fed back into the driver block. And using all these blocks and the data we collected, we could model the vehicle accurately enough so that we can evaluate how these vehicles perform in different drive cycles. That means in different scenarios. Here we can see the longitudinal equations of motion of a vehicle. On the right hand side of the image there is one force Fw, and on the left hand side of the image there are 4 forces Fg, Fa, Ma and Fr. Here Fg is the force needed to compensate for the road slope, Fa is the force needed to compensate the aerodynamic drag, Ma is the force needed to accelerate the vehicle with an acceleration of A, here m is the vehicle mass, and Fr is the force needed to compensate for the rolling resistance. On the right hand side of the image, Fw is the force available at the wheels in order to compensate for the 4 forces on the left hand side. And this force Fw comes from the vehicle's engine. Now, if you look at the equations, there are 6 equations in total here. The first 3 are the powers needed to compensate for the road slope and the power required to compensate for the aerodynamic drag, and then the power required to compensate for the rolling resistance. The fourth equation is the power balance, which we can then use in order to compute the vehicle's acceleration, and that can be used to compute the vehicle's speed profile and the vehicle's distance profile using the last 2 equations. Using the data we collected, we developed fuel consumption models of gas and diesel vehicles. Then we use these models to evaluate how these vehicles will perform for real drive cycles. This slide shows such a sample evaluation for a real life drive cycle. There are 4 plots here. The top plot shows the vehicle speed profile. whereas the second plot from the top shows the road elevation profile. The third plot from the top shows the energy consumption of a diesel vehicle and that of a gas vehicle, whether it's refueled by biogas, meaning biomethane, or CNG. And what we can see from the third plot is that if a gas vehicle is refueled by biogas or CNG, its energy consumption is about 20–30% higher than that of a diesel vehicle. This is because of lower energy efficiency of a gas engine compared to a diesel engine as of today. Now the fourth plot, that is the last plot, shows three different performance measures of gas vehicles compared to the baseline diesel vehicle. And from the first pillar on the last plot, we can see that when we look at the carbon emissions compared to a diesel vehicle, if a gas vehicle is refueled with biogas, or that is biomethane, then the overall well-to-wheel carbon emission is significantly lower, about 70–80% lower. Whereas if the gas vehicle is refueled by CNG, then the well-to-wheel emissions is lower, but around 10–15%. Now, when it comes to energy expenses, as we already saw on the third plot, the energy consumption of a gas vehicle, whether it's fueled by biogas or CNG, it's about 20–30% higher, caused by lower energy efficiency of a gas engine as of today. If we look at the third set of pillars, we can see that the fuel cost associated with a gas vehicle, if it's fueled by biogas, is about 30% lower than that of a diesel vehicle, which makes it attractive for fleet operators as they can reduce their refueling costs significantly, resulting in a break-even period, although the gas vehicles are a bit more expensive than that of a diesel vehicle. In the last slide, we saw model-based evaluation. In this slide, we will discuss data-based evaluation. To perform this, we collected data from 41 gas vehicles and 9 diesel vehicles over a period of 1 year when they performed transport operations around the UK. Then we used this data to compare these vehicles for different performance measures. On the top plot, we can see the well-to-wheel equivalent carbon emissions per transport work. That is, for a given transport work, how much emissions are made. And from the top plot, we can see that in the case of gas vehicles, whether it is refueled by CNG or biogas, their emissions are lower than that of diesel vehicles. To be more specific, if a gas vehicle is refueled by CNG, its carbon emissions is about 10–15% lower than that of a diesel vehicle. Now, if the same gas vehicle is refueled instead by biogas or biomethane, then its equivalent carbon emissions is significantly lower than that of a diesel vehicle by about 70–80%. Now, if you take a look at the second plot, we can see that the energy consumption per transport work is about 20–30% higher for a gas vehicle compared to a diesel vehicle. This higher energy consumption of gas vehicles is caused by lower energy efficiency of a gas engine as of now. Now, from the third plot, we can see that the fuel cost of a gas vehicle, if it's refueled by biogas, is about 30% lower than that of a diesel vehicle. This makes it attractive for fleet operators. From this slide, we can see that the total cost of a gas vehicle fueled with biogas breaks even with that of a diesel vehicle in about 2 years' time. By total cost, what I mean here is the capital cost plus refueling cost. This is attractive for any fleet operator. In conclusion, from this project, we figured out that compared to a diesel vehicle, a gas heavy goods vehicle will consume around 22% more energy. Whereas when we refuel a gas vehicle with biomethane, the refueling cost is about 30% lower. When we refuel a gas vehicle with CNG, the emissions are about 10% lower, whereas if you refuel the same vehicle with biomethane, the emissions are significantly lower by about 78%. And the break-even period of a gas vehicle is around 2 years, which is attractive for fleet operators. However, there is limited availability of biomethane.